Okay. Okay. So what's on the menu today?
Well, I'm very disorganized. We're gonna we don't know. I mean, it's gonna be very it's going to be very
What kind of
interactive.
restaurant is this?
Well, so okay, so my homework assignment was to basically try to come up with a nice Tannakian proof of Artin reciprocity.
Yes.
And I don't have a clean proof of that yet, but I want to talk about my attempts in that direction anyway, and then possibly after that, I'm not sure. I might talk about ridiculously ambitious stuff, but I might not even have time to talk about the ridiculously ambitious stuff. But so let's see. So right. Part of the reason I'm disorganized here is because I did discover stupid mistakes I was making and things like that. Like
I don't
yeah.
Excuse me, I don't mind hearing about those, because even if you say they were stupid, they were probably interesting.
Yeah. I mean, I will be talking about those, but so right. First of all, let me try to state not the full version, not a full version of Artin reciprocity theorem, but I'll state sort of a special case of it. At least I think this is a special case of the Artin reciprocity theorem. So I'm thinking of this as the Artin reciprocity theorem for well, for what we've been concentrating on, for Z mod 3 torsors. And so how do I try to state this? I'll try to say that let K be a number field. Then we can what's the word I'm looking for? Define or characterize or something like that. We can characterize the Z mod 3 torsors over K in two equivalent ways. And the theorem, this part of the Artin reciprocity theorem is basically the statement of the equivalence between these two ways of characterizing the Z mod 3 torsors. And so one of the ways will be what I'll call the Tannakian way. But again, this is, you should be careful trying to figure out how my usage of Tannakian compares to other people's usage of it. The other way, I guess, would be the Frobenius pattern way. Well, so let me describe. I'm trying to decide whether this qualifies as one of the stupid mistakes that I made that I was talking about, but it probably does, or just an omission of some kind or something like that. So I think I sort of fell into some stupid traps or some clever traps. I stupidly fell into some clever traps by overly focusing on the case where K is the rational field. And I failed to notice that a whole lot of the fun is really, or I took insufficient notice of the fact that how much of the fun is involved in really letting K vary, letting K vary. Well, so I haven't so far on this whiteboard, which is, again, this is a little bit of a cramped whiteboard, but I haven't explicitly said what the Tannakian way is and the Frobenius pattern way is, but I'll probably have to write that on a different page of the whiteboard because, as I say, it's a little bit cramped. And so we're going to have a canonical bijection here of some kind. Actually, now that I think about it, is bijection going to be the exact right word? Maybe it'll be more like an equivalence of categories. I don't know. I guess it'll probably be a canonical bijection if you look at it the right way. Or maybe if you look at it the wrong way, it will be. So maybe what I'll do right now, before even finishing the statement of these equivalent ways, the Tannakian way and the Frobenius pattern way, maybe I'll experiment with an example here. And I'll deliberately experiment with an example where K is not the rational field. Now, one of the things that we know is that when you're studying Z mod 3 torsors, that you are inexorably drawn into getting involved with the Eisenstein field, the Eisenstein rationals. But for that reason, it seems like a good idea not to use the Eisenstein field as an example here. Let's not choose K to be the Eisenstein field. That'd make, we've already sort of thought about that, and that's built into the whole problem, but we don't want to do that. So let's just use K to be the Gaussian field.
Okay.
An example. Okay. So so let's go to a new page here. So we're thinking about Z mod 3 torsors over the Gaussian field, over the Gaussian rationals, or whatever we call it, the fraction field of the Gaussian integers. I guess I'll notate it as the Gaussian rationals or something like that. And well, so let's think about let's experiment with the Tannakian approach here. Okay. So the Tannakian approach is that the representation category of Z mod 3 is basically generated by a single two-dimensional representation, but you can think of that two-dimensional representation as a sort of formal Eisenstein line object. Right. So, I mean, there's this Eisenstein line object L, And in this case, right, Eisenstein is not an Eisenstein line object is not a line object. It's actually a two-dimensional vector object, but it's a line object over the Eisenstein field, if you like. Well, and you know, and we've tried to sketch how this theory works. So we're going to have, you know, like L tensor to the third power over the Eisenstein field. And that's going to be, you know, have this frame or whatever we call it. I don't know which way I usually draw it. Maybe it goes like that. It's an invertible morphism.
Is that E, big E, supposed to be an L? No. What's
no?
E? Oh, E is the.
E is the formal. E is, you know, and this is right. And this isomorphism is supposed to be E linear. E for Eisenstein. And
I'm getting mixed up. So
yes,
so is
yes.
E are both. Is E an Eisenstein line object?
Yes, it is the trivial. It is E is the trivial Eisenstein line object.
Okay, so L is just some variable one.
L is an object variable. Yes.
Okay.
And you know, I could have written this. I could have emphasized this for some silly reason as E being the zeroth tensor power over E of L. But you know, it's just the unit object, which is E itself, since we're doing tensor product of Eisenstein line objects.
I think you said something like the category of representations of Z mod 3 over K is generated by
yes
the representation. And I thought you meant L, but now I'm thinking you mean E.
No, I mean L.
So it's generated by, so this fixed representation category is generated by a variable Eisenstein line object, meaning any one of those is going to generate it.
What do you mean, any one of what?
L's.
I mean, L is a formal variable here. I mean, we're just, you know, it's a generator, like it's a categorized version of a generator of a commutative ring. So I don't know. I mean, you're talking about all the different values it can take when you.
I thought L was an object in vect K.
No, it's E is an object in vect K. And I want to I'm sketching a theory here. This is, you know, sketch of the theory of a Z mod 3 torsor.
Okay.
But again, by abstract nonsense, theory of a Z mod 3 torsor can be thought of as a long-winded way of saying the representation category of Z mod 3. And because of the context that we're working in here, it's, you know, representations over Q, representations over the rational field. And in that context, this representation category is basically I want to say that it's like a, you know, sort of rational 2 vector space with sort of a basis of 2 irreducible objects, one of which is one-dimensional, that's the unit object, and the other one of which is this two-dimensional generator L.
Okay. But now you're not doing the rational case.
Say that again. Now I'm not doing what?
Doing the rational case. Now you're doing the Gaussian case.
Can I think of what you're saying? I mean, I'm still thinking of the theory. I mean, we're going to hum this theory. We're going to hum the same theory, but into the universe formed by Gaussian vector spaces instead of the universe formed by rational vector spaces.
So E is so E is an object in the rational vector spaces.
Yes, that's
Okay.
right, and it's
I think I said
two-dimensional.
vect K, and you agreed with me. Okay,
Vect K. Oh, what is K? You might have
K is
taken me
your
because I
field
didn't
that
see a
you
K
define.
here.
Oh, you did find it on the last page.
Oh,
K is
What?
Q Gauss, but
yes. Okay.
Okay.
So you did trick me. Yes, you did trick me. I failed to notice that K is Q Gauss, and right, you said vect K, and I should have caught that. Right.
Yeah.
But I did
Okay,
not
I
catch
think
it.
I get it. So so
Okay.
far, Q Gauss is not even.
That's right.
Except in the headline.
That's right. That's right. That's right. That's right.
Okay, so this thing is the thing we've been talking about before. Okay, yeah.
That's right. And yeah, and let's just and the other important thing is that, how does it work? There's this right, you take the formal Eisenstein conjugate of this thing, and you take the tensor square of this thing, and you have an isomorphism between that. An isomorphism between those two things.
I'm getting confused. You have that in
Yes.
addition to the isomorphism you just wrote down?
That's right. That's right. That's right.
Hmm.
I mean, it has to do with the way that, we're thinking of this sort of, we sometimes call it a sort of descent approach to understanding what a Z mod 3 torsor is in general. That, a Z mod 3 torsor over a field that doesn't contain the primitive third roots of unity is going to work by, geometrically pulling back by this sort of descent method, right? I mean, we're geometrically pulling back to the Eisenstein field, or algebraically pushing forward to the Eisenstein field. And the Z mod 3 torsor, which doesn't necessarily, the Z mod 3 torsor, what am I trying to say? The representation category splits over the Eisenstein field. I mean, and, that's exactly where it splits. And that makes the description of the torsor, very simple. And in that case, it's right. That's what we just sort of wrote down. The idea that it's, the third tensor power of the line object is trivialized. But right, that was just the thing before it descends to where it's really supposed to live. Right.
Okay,
So,
well, I'm confused. It sounds like you're sketching theory and you've written down part of the sketch, and
that's right.
Okay, and you haven't written down the rest.
That's right. I mean, you could write down, I mean, the rest would be, there's going to be like a commutative diagram here. I guess these are going to be isomorphisms, is that right? Yeah, and what's down in this bottom row is the tensor square of the formal Eisenstein conjugate of the top row. But we've discussed that, you might want to rearrange this so that on the top row you have the tensor square, and on the bottom row you have the formal Eisenstein conjugate, or whichever way you prefer to arrange it.
Mm-hmm.
And right, and these vertical arrows here are supposed to be induced by, right, they're coming from a morphism, they're coming from an isomorphism between L I want to say right, we're going to have this thing between L and L tensor square over E, and then I want to say formal Eisenstein conjugate or something like that, which I'll just notate for the moment as a bar. Or again, maybe I should put the bar on the top one or something like that. Let me just try that. And then you'll have this thing here, which I don't know what we call it. Maybe we call it A or something like that. And then, that determined, right? And then the actual vertical arrows that show up in the commutative square, those are the appropriate tensor powers and or formal, I guess just the appropriate tensor powers of A. So this would be, like the third tensor power of A over E, and this would be the 0th tensor power of A over E, which is really just 1.
Is that literally right, or would that be right if you stick the bar down on the bottom? That is, you don't.
I think it's right either way, except that you have to. When you don't have the bar here, it's going to end up being formal Eisenstein conjugation. It's going to be, from E to E, this involution that switches the two primitive third roots of unity.
I'm just wondering why you've got an L bar over on the right.
Yes, that's what I'm saying. I'm yeah.
Huh?
All right, so maybe you want it like this. Maybe you want it like try and get my eraser here. You want the bar on the bottom, I think, is what you want.
I think that's what I want, just because in your commutative square,
yes,
the bar on top.
That's right. I was trying to get away with being sloppy like that by having it, because it is right. It's more elegant when you have like the.
Yeah, I get why you wanted to do what you wanted to do, but I'm just struggling to figure out what's going on.
Yeah, sorry. Right. So because we're not really talking about the Gaussian thing yet, this is really just supposed to be a review of the Tannakian description of a Z mod 3 torsor. And right, and there's still details to check here, and the details sort of have to do with interpreting the notation, mostly. Making sure that this really is a correct sketch of the representation category of this group over the rational field.
Okay.
So
I'll leave it at that. Yep. So anyway, you've got this sketch of the theory of Z3 torsors over the rationals.
Yes,
Oh,
and
you're
now
doing
we can harm it into any universe U, which might end up being, ordinary rational vector spaces, or it might end up being Gaussian vector spaces, or whatever, or complex vector space. But we've talked about the idea of making the description of the groupoid of models of this theory in some universe U, making it more concrete by thinking in terms of sort of gauge fixing. And that's good, and that's part of the descent idea. But maybe we should actually try to think a little bit more conceptually about this gauge fixing phenomenon.
I was hoping that you'd first say, like, what's the grand plan here? So, like, you seem to be like hinting that we might take this theory, I guess, really doctrine. No, theory. This theory. This theory, and somehow do something to it to get the theory of Z mod 3 torsors over the, for example, the Gaussian field. So, like,
that's true. That is something you can do. That seems like an unnecessary complication at this.
What? I thought you were trying to describe the theory of Z mod 3 torsors over Q Gaussians. I mean, what's it doing there on the top of the page?
Well, I mean, it's just a matter of an internal harm versus an external harm.
Anyway,
you're suggesting,
I don't understand it all. So I just want to see what any of this has to do with Z mod 3 torsors over the Gaussians.
Well, you take this theory and you harm it into the Gaussian vector spaces.
Okay, that's what I was hoping.
And that's this external harm. That's this external harm. But you also hinted there that you could take an internal harm, instead of, where, right? If the external harm is you've got this theory and this other theory, which is the second theory, we call it a universe. We're harming from the theory to the universe. And we get a groupoid of models. Or actually, we in general, in this context, we actually get a category of models. So these are bi-categories. So the external harm is category value. The external harm is category value. But the internal harm would be theory value. And you sort of hinted at that.
You're just you're just intelligently reading some meaning into my remarks that was not necessarily there. I won't completely disavow it, but I was trying. I mean,
it's very interesting, but it's a little bit too advanced at the moment. Yes, go ahead. Okay. Yes.
So we're just going to get the category of Z mod 3 torsors over the Gaussians from this.
That's right.
Okay.
That's right.
Okay. But yeah, okay. Well, now I do agree with your claim about what I was thinking.
Right.
That I want to get more than the category. I want to be back on the same level that we were at, which is these whatever total 2 rigs or whatever the hell these kind of theories that we're talking about.
I mean, are you asking me to do that right now? I mean, we've already.
No.
I mean, I admit that already is hidden in the fabric of this. I mean, we were already doing that with the Eisenstein field in a way, but there is some internal harming into the universe of Eisenstein vector spaces here. That's why our sketch talks about the Eisenstein field in this formal way. And if we did that internal humming with the Gaussian thing, then we would be talking about the Gaussian field in a formal way. We were talking about, we'd have this internal version of the Gaussian field, just like we have this internal version E of the Eisenstein field. But at this moment, I'm treating E in this internal formal way, but I'm treating G in this external way. It's just, it's
G is the Gaussian.
yeah, G is the Gaussian field. I'm treating the Gaussian field just as this external thing, except that I'm not really treating it as a field. I'm just thinking about its vector spaces as a theory or for a universe. Yeah,
that's fine for now.
Okay.
Figure out what's going on.
Sure. And right, and then we talked about this gauge fixing method of making this category of models more concrete in some way, and that gauge fixing way had to do with the idea that when you actually have line objects in a vector space category, that you can always just think of them, you can gauge fix them to be the unit object, or it's the base field itself if you're working over a field. And when we did that gauge fixing thing here, that sort of turned. Did I ever give a name to this one? I meant to call this F or something like that. I thought we did call it F at some point. I'm not suggesting that's a great choice of letter, but I think that's what I'm calling it at the moment. F and then A and F. So F and A, when you gauge fix, they just become quantities or something like that. And am I saying this right? Where does the cube root coming in? Why am I getting mixed up between cubes and cube roots here? So what am I trying to say? So when we gauge fix, why does this give us this idea of cube roots here? So we're saying that we have a, well, I guess it's because, right, it's because of the, right, it's because of the morphisms between these models. So the morphisms are, right, prism diagrams between these commutative squares. And right, we've talked about how this gauge fixing kind of turns this into cube roots. Is that totally unclear? We need to go through that.
Not totally unclear. Yeah. You could.
I just confused myself with it, so maybe
totally
I could also.
Yeah. No, I think I sort of remember that whole spiel. I mean, so you could assume I remember that until
Okay.
doing something with it.
Okay, well, I think I'm now going to give another perspective on that. So maybe this other perspective will be helpful or something like that. So the other perspective that I'm going to try to give now is to think of this gauge fixing process, to think of it as explicitly taking place at the level of the theories that we're dealing with here. So what do I mean by that? Well, okay. So first of all, we have this theory. I guess I'll call it the theory of a Z mod 3 torsor. But its syntactic category is just the representation category of Z mod 3 over the rational field. That's how the notation is working at the moment. And now there's another theory that I can put down here, and I'm not sure what to call it. Maybe I'll call this one T prime, but maybe I'll call this one T.
Yep.
So we've got, T going to T prime. And T prime is supposed to be, if I'm not screwing myself up too badly here, T prime is supposed to be sort of this gauge fixing augmentation of T. So in other words, I'm just adding one additional thing to the theory, and that is a framing of L itself. So, if I put that in the sketch over here, it would just look like, well, I guess I have to, I guess I have to, off to the side here, or I just put the tensor unit. No, I guess I would put E. Is that what I'm saying? Yeah, well, I could say the tensor unit for Eisenstein tensor product. So that would be E. And this would be, I don't know, maybe I'll call it G for gauge fixing or something like that. So it's a gauge or something like that. And it is invertible.
One thing I'm confused by,
yes,
is that you seem to be acting like every line object is isomorphic to the trivial line object. Like, why do you get to do this gauge?
Well, you can posit anything you want in a theory. You can sketch any theory you want, right? I mean, right. That's why I talk about this whole idea of the belief method. You can believe in anything you want. That doesn't mean that it's true. Yeah.
No, but when you say gauge fixing,
yeah,
it's like something that could be true without really changing much. Like if I have a three-dimensional vector space, I can say like, let's pick an isomorphism to R3.
Well,
whereas but say I have a line bundle, let's pick an isomorphism to the trivial line bundle, then you're like really ruling out possibilities of what that line bundle could have been.
I mean, I might be doing something ugly or something like that, but I am, trying to prove a theorem, which I'm calling the Artin reciprocity theorem or something like that, which applies to number fields. So, right, I mean, fields.
Okay.
In those special.
Okay. So you're politely telling me that every line object in the vector spaces over a field actually is isomorphic to the trivial line object, and it's because
in those contexts that we're trying to prove a theorem about. Yes.
Yeah,
that's right.
But, I mean,
but you are making me feel like I'm doing something, like I'm not working internally enough or something like that, or you know what I mean? Like maybe there should be some more beautiful version of this where.
Well, no, anyway, you're always like reading my comments at like 2 levels higher than I.
Okay.
So, yeah, no, there's like some contexts where like it's really exciting how line objects aren't isomorphic to the trivial line object. That's the whole business about Picard groups. But okay, but
sure, and we're even dealing with that here. I mean, in this representation category, that's the whole point, that this, this L is not in the theory, in the syntactic category, there is no isomorphism to E. But we're going to believe in one. We're going to.
Now I'm even more confused. Okay.
Well, I don't know if what I'm trying here was a good idea. I mean, because we were, right, we had, I mean, what I said was we had this gauge fixing method and it was good enough. I think we understood it. We understood, how it worked, and it led to this cube root idea. But now I'm sort of suggesting, let's not leave good enough alone. Let's analyze this gauge fixing process in this way that involves this augmented theory T prime, which says, supposing you did have, supposing you do build into the theory this trivialization, this gauge fixing of L. And what happens when you try to think about the gauge fixing process from that viewpoint?
Okay. I'll hang on.
Oh, okay. So let's try to think a little bit about what this theory T prime is like. So it seems to me that it's really just like an affine variety. Am I screwing up here?
Sorry, I need to answer a phone call.
Okay, go ahead.
Okay, I'm back. Sorry.
Okay. So now I try to remember what I was saying. What was I saying? The T prime. Oh, right. I was trying to think about what T prime is like. What is this theory T prime like? And I was suggesting that it is simply an affine variety, if I'm not screwing up too badly. And the fact that it's a nice, simple thing like an affine variety is presumably part of what sort of makes the gauge fixing approach helpful. What makes it useful as a calculation device or something like that. Or at least I'm imagining that maybe that's the case. So,
So how does it get to be an affine variety? It has something, let's see, it has something to do with cubes.
well, I mean, the main thing is that it doesn't have any object variables in it anymore. We eliminated this object variable.
Uh-huh.
And so,
yeah,
all that's going to be left is basically these quantities. And I think all the constraints on these quantities, I think, are just going to be nice, simple equations. So I think we're just going to have a presentation of a commutative ring. The sketch is going to degenerate into a presentation of a commutative ring. And I want to say something like that. We can think of this. I mean, is that right? So what does that mean? What does that mean? What? I mean, what is going on there? Sorry, I'm getting confused here about orbit stacks. We started out with this theory that was very much kind of orbit stack. But we added more structure. So I sort of broke the symmetry down. I guess what I'm saying is something, I'm probably saying something very trivial like that. When you have an orbit stack, of the action of an affine algebraic group on an affine variety, when you have the orbit stack of that, then if you just take the original affine variety, then there's a morphism there. But which way does the morphism point, geometrically or algebraically? So geometrically, original affine variety projects down to the orbit stack, right?
Yeah.
Yes. And algebraically, it's in the other direction.
Can you tell me what those things are here? So
Yeah, I think that's right. Right. So yeah. So I think I'm saying that, T prime is the affine. Well, let's see. So T prime is the affine variety. And T is, the orbit stack. And the theory interpretation is pointing in this direction because this is the algebraic direction. This is the syntactic direction. So I think if I didn't make a sign error, this is fitting with what we said, that the original affine variety projects down to the orbit stack. Yes. So geometrically, the arrow is pointing upwards here, but algebraically, it's pointing downwards. And the orbit stack by what group? Well, it's something, I want to say it's something like GL1 over the Eisensteins or something like that. Yeah, it is. It's basically GL1 over the Eisenstein field, or whatever you called it, or GL1 over the formal Eisenstein field. That's a group here, and that's the automorphism group of the kind of object variable that we're putting in, right? We're putting in this object L, which is an Eisenstein line object. So that's, that's where this GL1 over the Eisensteins is coming in, or something like that. So,
and what's the affine variety?
That's a good question. It's going to be something. It's going to be something like, let's see. I mean,
Usually I would think like you start with an affine variety and then you mod out by a group and get this mysterious orbit stack. But here it sounds like you starting with this orbit stack and unwrapping it to this mysterious variety, which probably mysterious once you figure it out. But sounds
I mean, it's going to be something concrete about cubes or cube roots or something like that. What am I trying to say? It's going to be.
Yeah, I muttered something about that myself. I was thinking,
Yes.
But I couldn't figure out what affine variety is all about. So, I mean, you're trying to say,
yeah,
cube roots of numbers, mod.
Right. I mean, when we
numbers that are modulo the action of numbers that are cubes. That's what you're talking about. Sorry, these.
Yes.
Right.
Well, I mean, okay. I mean, right. So, I mean, well, right. Originally, it was these numbers with this, right, with this funny property that they are equivalent to their that they are equivalent to their Eisenstein conjugate of their square, Eisenstein square, or something like that. So yeah, in fact, right. I think what it's going to be, I think what this T prime is going to be as an affine variety, I think it's going to be something like a point in this affine variety, I think is going to be a number a quantity, a number, together with, well, sorry, it's going to be, right, it's actually going to be an Eisenstein quantity. So it's going to have, two coefficients. An Eisenstein quantity has two coefficients.
Uh-huh.
So it's going to be an Eisenstein quantity. So it has those two coefficients. And it's going to have a second Eisenstein quantity, right? So we're going to have these two Eisenstein quantities, F and A. And I think it's going to be I think it's going to be that, you know, the Eisenstein cube of A is going to be, you know, if you multiply that times the Eisenstein square of F, then you're going to get the conjugate of F or something like that. So let's try to write this down. Okay, so we're going to have like maybe I'll write it, you know, as a commutative ring. So starting from the initial commutative ring, which is the integers, and we're going to have these four generators. I think it's four generators. So F sub 1 and F sub, I'm tempted to say F sub, you know, 1 to the 1/3, but I think somebody has suggested to me that there's, you know, some reasonable abbreviation we can use. Is there like a sigma or omega or something like that? Or
Omega.
What does that look like?
A W.
A W. Okay, yeah, I can do a W. Okay, I know how to do that. So I'm going to call it W. Okay, and then it's going to be A sub 1 and A sub W. And then we put in these relations, these relators, that say that, you know, let's see if we can. Well, again, I'm going to put it in quotation marks because it's going to use sort of Eisenstein operations, but we can rewrite that without the Eisenstein operations. So it's like F1 plus FW times W, that thing squared times A1 plus AWW cubed is equal to, I think it's negative F1 minus FWW. Does that look like it's correct? No, I mean, the big question is, did I do the formal Eisenstein conjugation correctly? But isn't that thing on the wrote on the right-hand side of the equation? Isn't that the correct way to do a formal Eisenstein conjugation? You know, because
that looks more like a formal Gaussian conjugation.
No, I think it looks more like a formal. Did you see that? Because I have negative signs in front of both coefficients. Because, you know, all three.
No, but the coefficient of F1 shouldn't be changing. The conjugate of omega.
Oh, okay, maybe I did it wrong. Then okay, then maybe it's maybe I meant to say, okay, let me try it again. Let me try to fix that again. Okay, maybe it's negative. What am I trying to say? You know, I'm just trying to take advantage of, I'm just trying to write down, you know, how formal Eisenstein conjugation works. And I probably did screw it up. But I'm you know, it's something like that. All three of the third roots of unity add up to 0. So like, what am I trying to say? That, you know, we're trying to do this thing of W goes to -1 minus W or something like that. That's all I was trying to do. But so how do I write that?
So you still have an F1 with a no minus sign in front of it. F1 is not doing it.
Okay,
So-
okay. Sorry.
So there's that. Well, what you wrote is okay, but
Right.
I'd start by writing
I was
F1.
just trying to use the undo thing, and I got
okay, yeah.
okay.
Yeah, I see. You have to go back to that.
Yeah.
Sign.
Well, I could go forward.
Yeah.
Am I doing this right? Maybe I can't. Okay.
So F1,
F.
and
One
then
minus?
you're saying minus 1 plus omega. Is that what I'm just trusting you?
Maybe it's F1 minus FW. Is that what it is?
Yeah, well, that's it.
Is this correct?
Let's see. I'm believing you that omega bar is minus 1 minus omega.
Omega bar is, let me think. Omega bar.
I'll just draw a picture of it.
Yeah, draw a little picture somewhere. Where are you drawing the picture?
Oh, wow, I can actually draw it. Yeah, I forgot that I can actually. I was drawing it in my notebook, of course.
Oh, okay. I want you to draw the right board in like
Okay.
red or something like that. Or
Wait,
purple.
I don't even have.
Okay, there it is.
Oh yeah, well, I'm drawing with a mouse rather than I didn't have my tablet even hooked up. So
Oh, okay. Well, in that case, then maybe it's.
this is gonna look ugly. So this is 1.
Yeah.
This is omega.
Yeah.
This is horrible. Sorry.
Yes.
This is omega bar.
Yes.
And so let me just, I mean, sorry. It's interesting that it's really easier to do calculations when you can really write for me. So yeah, anyway, that's right. It's taking.
Yeah, I'm sorry, I'm horribly screwing up writing.
No, it's okay.
simple
It's fine.
formula.
It's fine. No, you're not. It's just I feel like doing the calculation in some stupid way. So yeah, so what you're just saying, like 1 plus omega bar is 0. So omega bar, like you said, is minus 1 minus omega.
Yes.
And so here you have the minus 1 part, and then you have the minus omega part. I think that's what I would do.
Okay. And I'm putting that thing in quotation marks because you have to expand that out in terms of the formal properties of W. W is just appearing here in a formal way. It's not really one of the variables or anything like that.
Yep.
And yeah, so I think that's this affine variety that we've got here. So like what dimension is that?
Should be 0-dimensional, but why do I no 1-dimensional? So because you're basically saying, what are you doing? I
mean, there is something interesting going on here in terms of this gauge fixing thing here is giving a geometric picture of the arithmetic. I mean, I'm always struggling to figure out, in what way is arithmetic geometry really geometry? But I have the vague feeling that, as I'm fumbling around here, that we are sort of getting close to understanding some of the way in which arithmetic geometry is really geometry.
So this is So you put in two Eisenstein variables, or
two or four.
Two Eisenstein variables and one Eisenstein equation.
Yes,
so like a one Eisenstein variable, one Eisenstein dimensional variety, but that's
right.
Really a 2-dimensional variety, since we're really working over the rationals.
Right, but I think it's sort of better to think of it as a 1-dimensional Eisenstein thing. Einstein 1-dimensional. And then when you take the orbit stack with respect to the TL1 over the Eisenstein,
Oh, but wait a minute, but is Eisenstein conjugation even, that's not an Eisenstein algebraic thing to do, right?
That's right.
I don't think you're getting an algebraic variety over in the
Okay, fair enough. Fair enough. Yeah, but okay, so it still is.
It's like a it's like a yeah, sorry, I don't know how to what to put it, like when whatever algebraic geometry becomes when you let yourself use complex conjugation, or
Yeah, something like that. But I think it is. Isn't it still? Yes, but that still does end up being two ordinary relators.
yeah, that is safe to say. Yeah.
Right. And then I think we are modding out by this, two-dimensional group, which is ZL1 over the Eisenstein thing. And so that probably is coming out to being a zero-dimensional orbit stack.
And that's probably supposed to be good because we're like back down to number theory or something like that.
Yeah, something like that. Something like that. I'm still trying to. I'm still fumbling around trying to figure out what I'm doing here. But again, we're looking at a different perspective on the gauge fixing process here. We're trying to look at a more conceptual, internal perspective on the gauge fixing process here. And the gauge fixing process here is supposed to be summed up in this augmentation of the theory that says, put in this extra gauge fixing structure that makes up, it changes a model of T into a model of T prime. I mean, my friend Emilio Faro, I still have the feeling that, gauge fixing, right? I mean, if you look up, what is it called, the N lab or something like that, if you look up evil in the N lab, first thing it probably says is gauge fixing or something like that. I have the right. I still have that feeling that gauge fixing is like evil or something like that. But it's like, I don't know. We're trying to take a good perspective on evil here or something like that. But I think it's also good to recognize, that it is evil. It is gauge fixing. And my friend Emilio Faro, the way I liked what he said one time, so I want to repeat what he said. I think he gave a talk or something where he was talking about the idea of, well, first of all, he's Spanish, because he likened gauge fixing to like some horrible thing that occurs in bullfighting, where you stick the sword like this, right? The sword or whatever that is that you stick into the bull, you torture the bull by putting in this extraneous thing. So I'm probably totally mangling his metaphor, but it was an apt metaphor when he described it.
Sounds like you'll enrage the mathematical object.
Well,
it will fight back even harder.
Well, but who will win?
Right. It will lose. Okay. Yes, that sounds very evil now. Yeah.
Right. So
you're reminding me of pinning down insects, pinning down butterflies or something like that. Yeah. You're like gauge fixing them.
Doesn't that, but somehow that reminds me of some terminology that you used to accuse me of using or something like that. What am I trying to say? Oh, I think I would talk about like nailing down, a degree of freedom, removing a degree of freedom by like nailing your foot to the floor or something like that. So you could only, rotate around that one foot or something like that.
Yeah. Well, that's nice. I'm very confused about a whole bunch of stuff, probably because I never continued thinking about the things we've been talking about on my own, which probably
right,
require me to actually write about them.
right.
So like I remember understanding stuff about these cubes, mod. Well, this sort of weird analog to these square free integers
Yes,
we're doing
yes,
here.
yes.
But somehow I haven't not really deeply understood it, apparently, because all this stuff seems sort of murky to me, because in ways that are not particularly your fault, and not particularly the fault of what's going on right now, but
Yes. I mean, I feel like I'm fumbling around and things are murky, but actually I am understanding some things better now. So it really sounds like I am claiming that this orbit stack, so take this affine variety and then think about the orbit stack with respect to that relevant group, and that orbit stack that really is, it sounds like I'm claiming that orbit stack really is like this model, this internal hum that we were talking about. This it's like a model stack of these torsors. I mean, it's this stack of these torsors, not just the groupoid, not just the external groupoid of these torsors or the external category of these torsors, but we're getting a stack of torsors here or something like that. Is that what's going on here? There's all sorts of good things here for me to think about and try to figure out if I'm, am I really on the right track here? Am I saying things close to correctly?
so so okay, so I mean, if what you're saying is right, then you're saying that, let me try to say it in a very humdrum,
Yes,
pedestrian way. So we would like to understand this, I'm going to call it, well, a 2-rig or theory of Z mod 3 torsors over the rationals. And we're gonna, one way to build it is to first come up with a theory which is really just taking the category, whose syntactic category, you just take the category of rational vector spaces and you just throw in some new variables, i.e. some new morphisms, not new objects. And that kind of theory is really just an affine variety in disguise. And you do that in this way that we've sketched here or described here. And then you mod out by GL1 Eisensteins. And then you get, sorry, you mod out in the stacky sense.
Yes.
And so then you get a theory that corresponds to a.
That's what I think is going on here. That's what I think is going on here.
Algebraic stack, and that's like the real thing.
Yeah, that's what I think. And this interpretation of theories that I wrote down here. So the process of going from T to T prime, that's, believing in some extra thing. But somehow this method of calculation, this gauge fixing method of calculation that we were talking about, which from some point of view has something to do with descent or something like that, that has something to do with the properties of this morph. Maybe that has to do with the question of whether this morphism is a descent morphism or a co-descent morphism or something like that. I mean, believing in something extra is going in this downward direction syntactically, but it looks like we're trying to get back somehow too. So like, you know, there may be some sort of co-belief process that goes in the backwards direction or something like that, and understanding how the descent works and when it works may involve understanding the interaction between the belief direction and possibly this co-belief direction in the other direction. But I've thought about this co-belief idea before. I think it actually does turn up somewhere, but
So is co-belief like you're just like pretending something for a while?
I don't know. I don't know. It's
You're making me think of suspension of disbelief.
I mean, I've thought about this, but I don't have good, you know, I mean, you know, there's this whole story and, you know, associated with the belief idea. But I've thought about the co-belief idea, but mostly just formally, and I don't have, you know, good stories associated with what co-belief would really mean. But it's possible that it might be something that we might have to understand here if we're going to really try to understand how descent works, what descent even means. But all right. So a lot of this was just kind of, like I say, experimenting with a allegedly more conceptual perspective on this gauge fixing or perhaps descent method. But let's try to, in the remaining time, let's try to take a more calculational, experimental approach, like I say, to thinking about these Z mod 3 torsors over the Gaussian field.
Okay.
So and you know, one of the ways this is perhaps going to be more concrete, more calculational, is that we are going to, I think, we're going to be dealing with more like an external harming rather than an internal harming. So let's try this. Let's try this. So right, and we still are sort of groping towards you know, the expression of some version or some special case of Artin reciprocity in terms of an equivalence between two ways of characterizing what the Z mod 3 torsors are, as an example, over the Gaussian field. And let's try to do that. Let's again, this is fumbling around and experimental, but let's try it. So so if I understand what I'm saying, to the extent that I understand what I'm saying, it sounds like I'm saying that we should take I guess I should call them F1 and FW and A1 and AW, and I should have these be Gaussian quantities, Gaussian numbers, you know, elements of the Gaussian field, the field of fractions, the Gaussian, I'll call them Gaussian quantities. But you take these Gaussian quantities and you formally form these Eisenstein quantities for them. So, you know, we have like F1 plus FW times W and A1 plus AW times W. I'm trying to remember to call it omega, but I just keep on forgetting. I just call it W. So maybe we should just stick with W for now. So yeah. And then we had this ridiculous equation. Right. We're just right now. I guess we're just taking these. We're taking these. Yeah. We're right. We're taking these things. Right. I mean, right. These are what there's a sort of hybrids of Gaussian and Eisensteinian quantities. Sort of formally Eisenstein, but meaning that they have these Gaussian coefficients. And of course, it turns out that you can actually. It's probably all sorts of games connected with flipping it around and thinking of these things as being formally Gaussian and concretely Eisensteinian, but that's not what I'm trying to do at the moment. Okay, so and what am I? Well, so first of all, interpreting these things as torsors has something to do with taking these cube roots of these things. Taking these cube roots of these things. And right. Okay. And then we have so we have this.
I mean, you can call them like F and A, those big fat things, and you can write down your equation.
Right.
Efficiently in terms of those.
Right. So what is it? It's like F. What is it? F.
I was
squared
times squared. Yeah. A cubed is F bar
times A cubed is equal to F bar. Okay. And I hope that's correct. And right. And now the idea is that if we right. So what am I trying to say? I'm trying to say something like that. I'm trying to say something like that. Let me think about it for a minute. Don't tell me the answer yet. Not yet. I'm trying to say that. Say that. F A. So right. Okay. So what we want to do is we want to think about something like the Gaussian integers. And we want to think about some homomorphism to a finite field. I'll call it H or something like that. And I'm trying to say that I'm trying to figure out where this, sort of congruence pattern thing is going to come in here. That maybe I should really write it like this. Let's see. Sorry. Okay, so we have some quotient ring of the Gaussian integers. And that's either going to be, that's going to be f sub q. It's going to be well, I'm really thinking about the case, right? Except for some ramified cases or something, this is going to be a finite field. And it's going to be, so it's going to be f sub q, where q is either a prime or a square of a prime. Right, because the Gaussian integers isn't that complicated as a field. That's as bad as it gets in terms of what its quotient fields are like. And so what am I trying to say here? I'm trying to say that, well, so this thing up here is supposed to be our first Tannakian way of classifying what the Z mod 3 torsors are. But the congruence pattern way, or the Frobenius pattern way, or the splitting pattern way is what? It's going to be, I want to say something like, well, so in general, for understanding Artin reciprocity theorem, we really have to worry about things like the possibility that J could be a non-principal idea. But that doesn't happen with the Gaussian integers. All ideals in the Gaussian integers are principal ideals. So I can perhaps somewhat evilly exploit that knowledge at the moment. That so what am I trying to say? That we can talk about J. Well, I can think of J as just being a Gaussian integer now. That just generates a Gaussian idea. And so I can talk about its congruence properties. So, I can talk about J being congruent to J prime modulo J double prime or something like that, where these are all Gaussian integers.
Yep.
And what am I trying to say here? I'm trying to say something like, I don't have the right way to say it yet, but you can, have fun watching me struggle trying to say it here. That, right, we've talked about this idea of cube-free, this, right, and sort of a joke, we've talked about this idea of cube-free integers or something like that. But now I think we're talking about something like cube-free Gaussian integers or something like that. Yeah, so it's right. I mean, and right. So this is even more of a joke than the previous. I mean, what am I trying to say? It's like maybe I'm saying that we should take the GL1 over the Gaussian field and mod out by the cubes in that. Maybe that's what I mean by a so-called cube-free Gaussian integer.
That would be pretty
Uh,
clear interpretation. Yep.
Yeah, I'm not sure I'm saying it exactly correctly, but yeah, but I think that's what I'm saying at the moment. And that would be if I'm not screwing up too badly, that would be a very lowbrow description of this second characterization of the Z mod 3 torsors. That's the second characterization involved in thinking of the Artin reciprocity theorem as being an equivalence between these two characterizations. So that would be the second characterization. And then we need, some explicit equivalence or explicit bijection or something. Right, it's probably going to be like an explicit equivalence of categories or something like that between these two alternative characterizations. And that's what we have to work out here. So how am I going to do that? I mean, I want to say it's going to be something straightforward, that we have the Tannakian description and then this congruence description. And I want to say something like that the equivalence is just going to be given by I want to say something like that you just push forward the torsor from the Gaussian integers or the Gaussian rationals. I'm being sloppy about the difference between them because I'm trying to sweep ramification issues under the table. You just push forward the torsor from the number ring or the number field. You push it forward to the finite field. And I mean, that's supposed to be giving us the equivalence. Is this making sense? Let me think. I mean, my more particular homework for right now we're sort of quitting. And we're quitting on this note of uncertainty that I'm not quite sure how I should be saying this. I'm still trying to express special case of the Artin reciprocity theorem. But I'm not clearly stating it yet, but maybe you can see what I'm trying to do here. I'm trying to clarify these two equivalent characterizations of what the Z mod 3 torsors are over, for example, the Gaussian field. And then I'm just trying to describe how the alleged equivalence between the two characterizations is supposed to work. And it's supposed to be a very tautological equivalence between them. It's just like you take the torsors over the number field or over the number ring, and you just push them forward to the finite fields, and that's going to give us the equivalence. But I'm not stating this clearly enough yet that we can really see very clearly how it's working. And I'm not sure if there's going to be any extra twists that we're going to throw in that are going to make it somehow less tautological and more calculational or something like that.
I mean, the more calculational, less things that could pop in there are like all this idea that how prime split depends in some periodic manner on their, well,
Yes.
periodic.
I mean, that's going to show up, but again, I think it's going to be very tautological in some sense. But what am I trying to say? That
I was going to say two. Well, that's
go
one.
Go ahead. Yeah,
That's one. And the other
go ahead.
thing is that right now you're doing a case where this Gaussian case where there's no ideal class group.
Right.
The ideal class group is a thing in Artin reciprocity. So
That's right. And yeah, and that's one of the things I'm a bit confused at right here. I mean, again, when I was doing this whole thing over the integers instead of over the Gaussians, for example, everything sort of seemed too tautological. It's so tautological that it was hard for me to say things that they were just too tautological or something like that. But now that I've moved to this Gaussian example, it seems to me now it's clearly not overly tautological. I really need to say this. I need to figure out how to say, rather than having multiple ways of saying it that are all equivalent, I need to figure out some way to say what is this equivalence between the two characterizations. And then I'm really confused. I'm still really confused about how this will manifest in the case where there are non-principal ideals. I'm just not seeing that clearly yet. So yeah, I really have to work on this. And one other thing that I don't think we've quite said out loud yet, but we've almost said it out loud yet, is that when you classify these torsors over the finite fields, that you classify them by these, one way to classify them is by these Frobenius elements. So that's going to be another calculational agreement, a calculational ingredient that's showing up here. So like, these Frobenius automorphisms are very explicit Pth power automorphisms of finite fields. And that's going to be some ingredient in these congruence patterns or something like that. But I'm not sure I have anything more intelligent to say at the moment. I think I just have a lot of homework that I have to go home and try and work on. And then and we didn't get to any of the more ambitious stuff today, which is probably just as well. But I have some, maybe it's not that ambitious, but it's for me it's ambitious. I have some more ambitious stuff to tell you about just basically just about trying to understand the Langlands program in some generality. And it's ambitious for me at this point because I don't really understand it, but I have some wild guesses to tell you about, but we didn't get to that today. Okay, so thanks a lot, and I'll see you.
Yep.
Okay.
I'll see you.
Okay.